questions, by the way, they're on those links, those screencasts that I sent you. So if you want to go back and review this for whatever reason, you can come see me, or you can look on that if you like, if that helps you. Let me see. We'll do this example in just a bit. But let's do a few quicker questions. Does anybody know which one we left off with? What number? 2.9b? Oh, those, yes. This one. Alice and Bill are at the top of a building. Alice throws her ball downward, but Bill simply drops. Which ball has the greater acceleration just after release? Alice takes her ball and she throws it, and Bill just drops it. Just after they leave their hands, which ball has the greater acceleration? So you ask your neighbor on this. You might think you know the answer when really you don't know the answer. So ask your neighbor on this, because there's a dichotomy going on in the class. All right, we'll just do about 10 more seconds. Y'all are doing a lot better now, by the way. I'll stop at 108. 108. Okay, awesome. I was even joking. That's good. So neither, they both have the same acceleration. At first, though, a lot of you put what answer? A, right? Because Alice throws hers down, and while it is true that while Alice is throwing the ball, it's accelerating, after it leaves her hand, the only acceleration it has is that due to gravity. So after both balls leave Alice and Bill's hand, then they're both going to be accelerating at minus 10 meters per second squared. All right? Let me tell you a little paleontology. I know this isn't a geology class, but do you know why you can never hear a pterodactyl go to the bathroom? This has baffled geologists for centuries. Y'all know why? The P is silent. Go tell your favorite middle schooler, they'll like you. So they both have the same acceleration. Which one has the greater velocity when they hit the ground? Alice's, right. And that's why you thought it was Alice's. She has a greater velocity with her ball, but not greater acceleration. You throw a ball upward with an initial speed of 10 meters per second. If you assume there's no air resistance, what is its speed when it returns to you? We talked about this with free fall motion, one of the aspects of free fall motion. Free to ask your neighbor if you like. I'm going to stop at 55, so just guess if you're not sure. Remember on these questions, even if you guess and get it wrong, you still get some credit. Okay, B is right. Remember when it comes back to you, it's going to have exactly the same speed as what it left. So if that throws something up and then it comes back down, if it's 10 meters per second here, the speed is actually going to be plus 10. Over here, it'll be minus 10 meters per second, the velocity. Maggie?
I thought when you throw something up and it comes back down faster. And
No.
You gave that example, but
I think I said the opposite of that. That when you, if I did, that's not what I intended to say.
Okay.
Sorry. If it goes up and when it comes back down, it's going to be going the same speed.
Okay.
All right. Now in cartoons and what have you, that's often the case that They go up really, really slow, and then they sort of hang out at the top for a while, and then they do what? And then they drop down. But that's not real life. That's like, animated world. That's what, Marco? Looney Tunes, right? That's Looney Tunes world. But in real life, it's going to have the same speed. And that's ignoring air resistance. But air resistance, it's not really that big of a deal, honestly. When you're dealing with small things that are regular, like smoothly shaped, it's not a big deal. You drop a rock off a bridge. When the rock has fallen 4 meters, you drop a second rock. As the two rocks continue to fall, what happens to their velocities? Do about 10 more seconds. Stopping at 40. Okay, good. A is the right answer. Well, let's look at these others because a number of you had these others as well. They're both going to increase at the same rate. That means they both have the same acceleration. If you look here, the velocity of the first rock increases, faster than the velocity of the second. When I say that the velocity increases, that's talking about the acceleration. The acceleration describes how the velocity changes. And here the velocity will change at the same rate. I drop one rock, I wait, and then I drop a second rock. They're going to be going different velocities, but they'll both have the same acceleration. So the velocities will be changing at the same rate. So that gets rid of B, C, and D. The velocities are not going to stay constant. It has to be A because they have the same acceleration. The graph of position versus time for a car is given here. What can you say about the velocity of the car over time? Make sure you're good on these because you're going to see a couple of them on the test, where I give you a graph and ask you to describe the motion, or describe motion and ask you to pick the graph. All right, I'll stop at 102. 102. I'm not going to show the answer because I want you to try it again. But first, the what of a position versus time graph gives us the velocity. The slope. So when I ask you about the velocity, really what I'm asking you about is what is the slope of this graph doing? And let's see, y'all were sort of spread out. About half of you got it right and half of you got it wrong. So let's try it again. What we're asking is, what is the slope of this graph doing all the time? Is the slope increasing all the time? Is the slope decreasing all the time? Is the slope remaining constant? Is the slope increasing sometimes and decreasing sometimes? All right, don't put E. All right, don't put E. It's safe for D. E might be true, but don't put it. You can ask your neighbor what they put, too. What is the slope doing? All right, I'm going to stop at 1 minute. 1 minute. Okay, B is the right answer here. All right, the slope here initially is big and positive, and the slope gets less as time goes on. So it's going to slow down all the time. Initially a big slope or a big velocity, and then later it has a smaller slope or a smaller velocity. There's the slope changing. Consider the line labeled A. So right now, don't worry about B. You're just looking at A. How does the speed change with time for that line, for line A? All right, I'll stop at 45. 45. Obviously, people have trouble interpreting graphs, and that's okay for you to have trouble now, but you need to spend some time on this and think about the graphs of motion, because you're going to see probably 3 to 5 problems on the test. It's going to be a big deal, so make sure you go back and look at those old tests if you're in one of these, 30% of the class. Okay, so here, line A, how does the speed change with time? I look at the axes. I have velocity here, I have time here. As time increases, the speed increases. There's nothing tricky about not looking at the slope or anything. Here the velocity is such and such. Here it's a bigger value. Just looking at how it changes on the y-axis. Didn't really start using graphs till a couple hundred years ago. So before that, did we talk about this? People used to never use graphs. That was like part of the big deal with the scientific revolution, that all of a sudden they were able to visualize data and think about how it changes. And that was something that people had never done before. It really changed the way that we think about the world. Consider the line labeled B. Well, how does the speed change with time for line B? I'm going to stop at 30. So let's look at B. Here, B is what? Big or small? Or the speed is big or small? It's big, okay, it's big. And then as I go along here, it does what? It decreases. What happens here? It goes to 0, right? And then it starts going in the negative direction. So the value does become less, like it becomes more negative, but the speed is increasing. This, by the way, this is a graph of this motion. Throw something up, it goes to 0, and then it comes back down. Slows down, speeds up. Slows down, speeds up. You're getting very, very sleepy. Oh, you are sleepy. All right, so E is the right answer. Good job, the 22 of you who will now all stand up and think about. No, that's a joke. Don't do that. Think about these graphs, what they're showing. Let's look at some. Oh, I just gave this answer. That's okay. All right, I will stop at 50 seconds, or 53, let's say. Okay, good. D is right. That's throwing something up and coming down again. It's the plot that we just looked at. Initially big positive velocity, zero velocity, big negative velocity as it returns to your hand. Also notice the speed here and the speed here, they're exactly the same. It comes back to the same speed with which it left. You drop a very bouncy rubber ball, it falls, and then it hits the floor and bounces right back up to you, which represents the V versus T graph. I have a ball, I drop it, and it comes right back up again. Those of you in lab, this is like the Y velocity for the bounce pass that y'all did yesterday. All right, I'll stop at 45. I had a good joke too, as a thing. That was a good one. All right, the answer here is D. I know why you put D, because it sort of looks like a bounce, doesn't it? But it's not right. If I have something, it initially is going in the negative direction, and it's speeding up. See? Speeding up in the negative direction. And then all of a sudden, it turns around and goes the opposite direction with a big positive velocity. And then as it goes up, it slows down. So the answer is D there. Okay, so listen, I know I have about 30 seconds left. There is a problem at the end of your chapter. We're going to skip that one. It's not terribly important. Let me tell you that you will not have to use the quadratic equation on the exam. And in that example, you have to use the quadratic sign. We're not going to worry about it. You hear what I'm saying? No quadratics. You will never have to. If you think you do, then you're wrong. You don't have to use the quadratic. Hold on just a second. Don't forget, like 15 seconds. On Friday, we're going to go into Chapter 3. I'll assign the homework today. I would recommend that you go ahead and at least look at those problems because they'll sort of get your mind going in that direction. It's sort of stuff that we've seen before with trig, but it's going to need a little bit of new stuff too. But I'll see y'all on Friday, okay?